Hey everybody, and welcome back to I Hate Chemical Engineering. This is our second video and first lesson in the Thermo series. If you're a chemical engineer, this would be Thermo 1 class. If you're not a chemical engineer, or you're like a mechanical, let's say, this would be your basic Thermo class that you would have that covers most everything that you would also learn. I'm going to be teaching out of Smith, Ness, and Abbott's Introduction to Chemical Engineering Thermodynamics textbook, the 7th and 8th editions. I'll be given practice problems from the 8th edition that also are in the 7th edition, so you don't have to worry about us, not covering similar material. So let's go ahead and get started. Today's lessons on thermodynamic state variables, and the Gibbs Phase Rule. So let's go ahead and draw us a box of fluid. So we got a box of fluid in here. So this is going to be fluid. Whoa. And if I was to ask you, what is, describe for me this fluid, you might say it's okay. This fluid's either a liquid, it could be a liquid, it could be or gas. You might say its temperature is in, degrees C or Kelvin or degrees Fahrenheit or Rankine even. Though we don't use that very often. You could look at the the volume of the fluid, right? So the volume. Volume of the fluid, so you'd be looking cubic meters or cubic feet or gallons. And then also you could be looking at the pressure of the fluid, right? So we got a lot of different things that we could be looking at here. So, and that's in pascals usually, or atmospheres, or PSI. If you're in America, usually we do things in PSIG or PSI absolute. So is that everything that there is to know about a fluid? Well, no, not necessarily. But I'll stop us right there and say that at a particular moment in time, if you know the temperature and the volume and the pressure of your fluid, all of that works in together to define what is the fluid state. So we're going to just have a definition here. So the state. The state is basically more or less the full description of the fluid. And you could say the fluid's thermodynamic properties. So let's just go ahead and say that. Thermodynamic properties. All right, so and write that out because it's important to understand what the idea of a state is. So, and then we have things that we call state variables. So a state variable are things that help define the state, right? So again, those are our temp. So we'll call that, let's change the color here. Temp for temperature, we'll use T. Pressure, we'll use P. I'll come back to volume here in a second. We'll look at phase. So phase can be in a lot of different ways. So a lot of times we'll see it done like this with this Greek symbol. Psi, and that represents the vapor fraction. So you could say vapor fraction. And that's in particular to liquids and gases. So we'll also look at solids in a very brief amount of detail, but most of this class is going to be looking at fluids. And then you got composition, right? So you could look at composition. And you can define that in a variety of ways. You could look at molar or mass composition. And then volume, right? So let's scroll down a little bit. We'll look at volume. So volume in thermodynamics is usually in specific or molar volume. So we're going to say specific or molar volume. And why is that? Well, most of the other terms that we're going to be looking at are in mass specific terms or in molar specific terms. So in other words, this volume is going to be in cubic meters usually per gram mole, or cubic meters per kilogram. Come on. I know that was a lot of space right there. But that's usually what we define as volume in thermodynamics. Every text is going to be slightly different in how they define this. So sometimes they use capital letters and lowercase letters depending on which term they're talking about. Sometimes they use what they call a hat, or it would be a caret symbol above the variable to indicate that it's a specific quantity. In the textbook that we're using, it just uses the regular capital letter to define the specific or molar quantity. And anytime that it's talking about a totalized version of a quantity that's supposed to be typically in specific or molar quantities, it'll always say have a superscript of a T. And that's not to the power of T, that just means the total volume, which again is a state variable of its own, but that would just be the regular cubic meters there. So we'll get rid of that though, but that's important to understand because that changes, the ideal gas law, which you've learned in basic chemistry, from PV equals nRT to actually PV equals RT. So you got to change your mindset from looking at earlier chemistry from high school to thermodynamics here. So keeping that in mind, we have other thermodynamic quantities that we want, or state variables that we want to know about, and that we haven't even discussed. So I'm just going to throw them up here. And these are going to be the ones that are going to be most important to you throughout your career as a chemical engineer. Most people don't even remember any of this, to be perfectly honest. But there's three or four, you could say, in particular that are worth note, right? So we're going to color these different because they're not typical. You've went through all of these other ones in school thus far. So first off, we're going to look at U. U is, or sometimes capital E, is known as the internal energy. We'll define that again in the next video, but to be brief, that is the total amount of energy that the fluid contains. That's not it's looking at the fluid as its reference point, let's say. So if the fluid, if this whole vessel is moving, with at 5 meters per second, it's not looking at the kinetic energy of the fluid of the whole, vessel and fluid altogether. But what it is looking at is the energy that are contained within the molecules, so of the fluid. And again, we're going to define that a little bit better in the next video. But I'm just trying to give a brief primer here because we got a little bit of material to go through. So other variables that we have are enthalpy. We have entropy. We have the Helmholtz free energy, which no one uses. And then we have the Gibbs free energy. And there's a bevy of others that we're not going to discuss because these are the most important ones. But what we will say is that all of these, with the exception of entropy, have energy per mole or per mass. So we're going to use energy per kilogram here just as an example. And that's for all of these except for entropy. And entropy has an energy per mass per degree, Kelvin typically. So, or degree Celsius, you could say. So, these are all the state variables that you're going to really be concerned with through the course. And you might be asking yourself, well, why do I need to know this? Or what these state variables are? I don't have any idea what enthalpy, entropy, Helmholtz free energy, or Gibbs free energy is. You may have touched on it in chemistry a little bit, some, in particular maybe Gibbs and enthalpy. And you've probably got an idea of what entropy is. It's kind of a fun kind of thing to discuss, I know. People always like to say entropy is a measure of disorder, but that's not technically correct. It is and it isn't. We're going to get into some solid definitions here in a second, or in a couple lessons now, because it's hard to just blanket statement some of these things. Internal energy is the one that's easiest to blanket statement because it's a solid definition. The other four are more esoteric. But it should be pretty straightforward to understand, hey, if I want to do an energy balance on a system, if I need to understand how much energy I need to put into this fluid to make it boil or change phase or separate or whatever you're doing, I need to understand how much energy I have currently. So how does one do that? Well, that's more of a topic for the next lesson, but what I can say to you today is if we understand the Gibbs Phase Rule, we can understand whether or not we're even able to calculate these other values. So the Gibbs Phase Rule is basically is a law or a rule, you could say, that determines how many degrees of freedom or how many variables do I need to know to be able to fully define my system. And when I say fully define my system, that means define a value for U, for H, for S, for A, for G, for psi, for X, and etc. So let's just go ahead and write it out in plain terms. So the Gibbs Phase Rule states the following. So the degrees of freedom, so sometimes you'll see it as capital F. Sometimes you'll see, a variety of different nomenclature for what this is. But the degrees of freedom, in other words, the number of variables you need to know in order to fully define the system, is going to be equal to 2 minus pi plus n. And you might be going like, what is pi? What is n? Well, n is the number of components in your system. And pi is the number of phases present. So, really straightforward. Let's go ahead and do an example of this. So I think I got to make another page. All right, so let's find a box here. Oops. Excuse me. So let's draw us a box. Let's put a fluid in it, and we will say, okay, it's just a fluid. It's a pure fluid. So one phase. So we'll say pi equals 1. And remember, our equation was degrees of freedom equals 2 minus pi plus n. And we'll say it's a pure component. All right, therefore, I need to know my degrees of freedom equals 2 minus 1 plus 1, which equals 2. So if I know two variables, so if I know, let's say, pressure and temperature, I will also be able to calculate through methods we've not yet discussed the volume, the vapor fraction, the composition, which we just already said was 1. So we'll go on to the next thing, the internal energy, the entropy, the enthalpy, the Gibbs free energy, the Helmholtz free energy. We'll be able to calculate all of that. Now, we usually say pressure and temperature because those are the most well-known variables or most easily measured. So, but also, if you were to start with, internal energy and temperature, you'd be able to calculate pressure or vice versa. Now, not typically done, but I'm just trying to give you an idea of that is possible. So let's do another example here. It'll be a very quick example, then we'll be done with the video. Let's say, for instance, we have a fluid. We'll have a pure fluid, so N equals 1, and pi equals 2. So we have two phases. So again, our degrees of freedom equals 2 minus 2 plus 1, which equals 1. Therefore, if we have a system that is of a pure fluid of two phases, all I need to set or know about the system is a single variable. So if I know pressure, then I can calculate temperature, volume, internal energy, enthalpy, entropy, A and G, Helmholtz and Gibbs free energies. But also, if I know temperature, I could calculate pressure, volume, internal energy, enthalpy, entropy, and the Gibbs and Helmholtz free energies. So I'm fully defined just by knowing a single variable. And that becomes fairly obvious if I was to say, okay, class, I've got water boiling. Let's say if I got water here. And I got boiling. If I told you the pressure, say pressure equals 1 atmosphere, you would tell me immediately, without hesitation, that that means the temperature must be equal to 100 degrees C. Right? Because you know the boiling point of water. Right? So if it's pure water at atmospheric pressure, it boils at 100 C. Now, that obviously changes as the the pressure changes. That also changes, what the specific volume is, right? So I'd need to know a little bit more about have a better calculation or correlation or some kind of equation to be able to calculate the specific volume. But what I do know, and what you have learned thus far up in your engineering studies, is that the vapor pressure is a function of temperature. Of a pure component, right? So if I can always know the vapor pressure of any pure fluid if I have a temperature. And we'll talk about that more later. But that's in part due to the Gibbs Phase Rule, or at least our understanding of the Gibbs Phase Rule. So we only need one degree of freedom, one variable identified in order to determine all the other things, all of the other state variables of our system. All right. So that's the Gibbs Phase Rule, guys. Next lesson is going to be on internal energy, to define more about what even is this and how do we do an energy balance. It's going to be a fun lesson. It's one of the more difficult ones to really grasp. It's really critical to grasp the energy balance and why we end up at enthalpy instead of internal energy. And but that's just a little primer for you guys. Appreciate y'all. If you enjoyed the lesson and want more, please like, comment, and subscribe.